In the last video, we talked about combining multiple torques on a single object, and I think we should see an example of that. So let's go back to our forever example, the wrench. So let's say we have a wrench that is turning some bolt about this point, and let's say there are two forces on this wrench. So let's say this is, we'll say again, this is a very big wrench. We'll say there's a force downward on it right here, and this is 8 newtons of force, and this distance is 0.5 meters. And then we'll also say there's another force on this wrench that is in the upward direction, that is 7 newtons, and this distance is 0.8 meters. So it's someone pushing down here with 8 newtons of force, someone pushing up there with 7 newtons of force, and we want to know what is the net torque about the left end, meaning, to calculate torques, we need a point, a rotation point that this is relative to, and that rotation point is here, our, center of the nut or whatever. Okay, so to figure this out, let's just label these force A and force B. So we have two torques, torque A and torque B. So each of these torques is R F perpendicular. Both of these forces A and B are perpendicular to the wrench, so we don't have to find any force components. Both of our F's are F perpendicular. And the R's we're given, right? So torque A here is at a distance of 0.5 meters away, and it is a force of 8 newtons. Torque B is a distance of 0.8 meters away, and it is a force of 7 newtons. Now, what we're going to do is we want to find the net torque, so just like net forces, that is the sum of all the torques on the object. In this case, this is the first time that we've had to think about whether our torques are acting in the same direction or opposite directions. And remember, we have defined, for the purposes of this class, positive torques are counterclockwise, negative torques are clockwise. So, on this image, about this rotation point, this force A pushing down will tend to rotate our object in the clockwise direction, which means this A torque needs a minus sign. Torque B, around this rotation point on the left, is going to push this up, that is counterclockwise, that is going to be a positive torque. Okay, so adding these up, we have torque A, which is minus 4 newton meters, and torque B, which is plus 5.6 newton meters. So we have minus 4 plus 5.6, which gives us plus 1.6 newton meters of torque. So this also tells us which one of these two is going to win, right? We have torque A and torque B, and the net torque is in the counterclockwise direction. So given these two torques, our wrench is going to rotate counterclockwise from this positive torque. So this is actually kind of an important result, because not only have we done this plus and minus thing to get the result, but there's a result that would not have been obvious a few chapters ago. And what I mean by that is we said that the wrench is going to turn counterclockwise, which means that this 7 newtons of force is going to win over this 8 newtons of force, right? We have 7 newtons up, 8 newtons down, and it's going to turn up. It's going to turn counterclockwise. And that's because even though this force is smaller, the torque of this one is bigger because it is acting further away. So there are a number of ways you would say this in everyday speech. The whatever's pushing it, B, has a greater mechanical advantage. Sometimes that term is used, or B is pushing with a longer lever arm. This is related to the idea of levers as mechanical objects. Anyway, so this is a good simple example of finding net torques. Okay, so this example was pretty simple. We were given the forces on this. So in analogy with our force problems, this is kind of like a chapter 3 force problem where, we know if we're given all the forces, we need to combine these quantities to find out what happens, right? That is different than chapter 4 force problems where we were given a scenario of skier sliding down the hill and asked to draw a free body diagram. So we want to be able to do the same thing for torques also. But as I mentioned in the previous video, where our forces are acting on our objects now makes a big difference, like we just saw in this example. So we need free body diagrams that preserve that information, that tell us where forces are acting on objects. So that leads us to a important tool for solving torque problems, the extended free body diagram. So the idea here is going to be the same as free body diagrams. We're just including this where the force is acting information as well. Okay, so these are a little different than our regular free body diagrams, so I'm going to give you kind of the step-by-step, similar to how we draw our other free body diagrams. Okay, so our first step is to draw the object as a line. So this is different than drawing the object as a point, which is what we have done for free body diagrams until now. So on this line, we want to identify the forces and the point at which they are acting on the object. Acting here means, pushing or pulling. And we are talking about forces here. These forces might be generating torques, but we're not there yet. We're just still thinking about this in terms of like chapter 4. Is there a string attached? That's a tension force. Is there a spring pushing on it? That's a spring force, and so on. All right, we also want to then identify the center of rotation, or the rotation point. I'll call it the rotation point. And I should say, this doesn't have to be a place where anything is actually rotating. It turns out this is more of a choice of convenience mathematically as much as anything else. So we'll say more on this later. And then after this, once we know our rotation point, we can calculate the torque that goes along with each force. And then maybe we're adding up all the torques to find the net torque or something, something like that. So this is our recipe for making an extended free body diagram. And let's, in the next video, we're going to see an example of using this on a torque problem.